Okay, welcome everybody. Can people still see my screen and hear me okay? All right, perfect. All right, we'll go ahead and get started. Thank you for coming to hear and learn about working with degree days and weather data and building decision support tools in R. So I'm Andy Lyons, and I'm pleased to be with you for the next 90 minutes or so, and then again, hopefully same time next week. Let me put in the chat window here the URL to these slides that we'll be going through. And then this also has, let's try that. Yeah, so this webpage will have links to all the materials that we'll be doing today, including the hands-on exercises, which will be done in Posit Cloud, which we'll get to that momentarily. So, but just go ahead and dive right in. This is a new workshop, so thank you for coming. Thank you for being guinea pigs in some ways, because this is a topic I've enjoy working with. But this will be the first time I'm trying to present it. So I'm here at the first set of slides, and we'll do intros here in a second. But yeah, we're going to be talking about working with degree days in R, and the focus of today will be generating the code that we can use to download weather data into R, compute degree days, and then use degree days in collaboration with degree day models to make predictions. All right, so that's kind of what we're talking about today. Let me talk a little bit about me first and my group. So I am with the Informatics and GIS statewide program. We are part of the University of California Division of Ag and Natural Resource System, as are many of you. And if you're not from California, or this is not familiar to you, this is a piece of the University of California system that provides research and extension services to the people of California, and with a focus on agriculture writ large and natural resources. So we are based out of the university system. That's kind of how extension is done in the United States. And we have researchers across the entire state of California, in off-campus and county offices. We have clusters of faculty on 5 of the 10 UC campuses, who have joint appointments with the campus department, as well as this other branch of the UC. We have 9 field stations that are doing also research and extension, and a whole bunch of these statewide programs, some of which are public-facing, like 4-H or Master Gardeners. Some of them are more research or policy-focused. And I am part of the Informatics and GIS group. We are essentially a GIS unit to provide geospatial and data science support to this entire network. So it's really fun. If anyone is interested in this as a career path, we'd be happy to talk more about it. This is my group here, most of which are on our meeting today. So we are a smallish but growing group of geospatial data science nerds, and we provide services to the ANR network writ large. We do all manner of drone services. We build maps. We help people find data, chug data, share data through websites, through decision support tools. We have a series of workshops that we teach, usually a couple times a year. A drone camp is coming up. If you're interested in using drones for research and mapping, we provide research services in drone, and then we teach it. And then we have office hours. So I invite everybody to sign up for office hours. They are open to workshop alumni. So if you have follow-up questions to today, which I suspect there will be follow-up questions, feel free to find our website and sign up for office hours to talk more about it. And this is my team up here. So yeah, it's a real privilege to be with this group. Talk a little bit more about people who registered. Seeing about roughly half of the registration people showed up, which is pretty typical. A lot of academics. So as expected, degree days, it's a bit of a niche topic. It's used in research quite a bit. So a lot of people from research institutions here, as well as nice to see some local, state, and federal government people coming here. So welcome everybody. Fantastic to have you all here. This is the institutions people are coming from through their from their email domains. So Davis is one of our campuses that has a lot of A&R people attached to it. So this is pretty typical. But again, nice to see a little bit of a spread there. This is a map showing where people are coming from. So it's nice to see we have a few people who registered from Germany. I recognize a couple of faces here. Big cluster of registrants coming from California. So that's great. We will be talking about California data sources today, and those will be the examples, but the stuff we're talking about here is pretty generic. Many people have heard about degree days. They may or may not know a lot of the details behind that. So we see kind of an even spread there. But I do know there are some real experts on working with degree days here today. So any of those hard questions, we'll share them back to the group. And this is a nice spectrum of people who are experienced with R, because we will be doing a lot of, I will talk through the functions that we're going to be using, but we will be using our functions. So it's great to see a good spread of people with R. This is also typical. We're seeing increasing backgrounds with R in our coming to our workshops. Okay, so the work we're looking at today, it's part of a thread of activities that my group has been engaged in for the last 2 or 3 years, working with weather data, climate data, working with open source programming environments like R and Python. And we have a number of projects in this vein, including the development of libraries to work with these tools. So today we're looking at R, and we're looking at a package that makes it easier to compute degree days. We also have some Python code available too that my colleague Shane Fire has written, both to compute degree days, as well as to download climate data from CalAdapt. So that's a library called CalAdapt PY. We can find the link and stick it in the chat window here in a little bit. So that's one of the things we've been working on, is kind of developing libraries. And then we use those libraries in projects, such as building decision support tools like what we're talking about today. Here's some screenshots of what we're going to look at. And then we're also working on developing some ebooks of code recipes. So essentially we're trying to develop tools that we can use ourselves, but that we can also share with the world at large, to make better use of these data and these models. Right? So we have a set of activities there. So let's talk a little bit about what we're going to work on today. So this workshop, the primary focus of this workshop is going to be programming methods and working with these data in R. Right? So that is the focus. Today we're going to be looking at methods for working with weather data in the second half of today, as well as computing degree days and working with the degree day model. So the bulk of what we'll be doing today, we'll be looking at some notebooks and running through notebooks with actual coding. So that is the focus of what we're looking at today. So we will look at, we'll talk a little bit about what degree days are, what degree day models are, how those two work together, how to compute these things in R, how to also make predictions based on what the models give us, and then how to visualize predictions. Because again, what we're working towards that we'll try to finish up next week will be some kind of decision support tool where you do want to present in a digestible manner the predictions that are being made with these models, whether that's through tables or charts. We will also talk a little bit today about what makes for good weather data. We'll talk about some weather data APIs or online resources for different time periods of weather data, because that's part of why what makes this tricky is that there's recent data and a lot of the weather models, if you're trying to predict, the degree day models, if they're trying to predict crop development or insect development, you need data for different time periods. The recent past, probably. There's short-term forecasts, like the next 7 days. And then if you're trying to support decisions that are weeks or months out, then you need to come up with some sort of estimate for the longer-term forecast. You might use historic daily averages for that. There are some seasonal projections out there, and we'll see an example of using one of those. You can also use these same models for modeled climate futures, so decades into the future, right? These same models are really, you can basically plug and play them into modeled climate futures, although there are some details there. We'll also look at today at calling weather APIs, including, there are a few R packages that make that pretty easy, right? You just write an R function and you hit enter and it fetches data from the weather API and you get it back and it's all tidy and ready to go. Unfortunately, there's a lot of good weather data APIs available today that there are no R packages available. So I'm going to show you also how to write your own code to query APIs using the HTTR2 package, which I'm kind of excited about. And then we're also going to look at, again, R methods to get the data that you grab from the API and then wrangle it, right? To put it into the columns and the rows and the structure that you need to do the next thing, which is probably going to be computing degree days or something like that. So data wrangling methods. And then next week, we'll talk about Shiny apps, right? So Shiny is an R package that you can use to create a lightweight HTML web interface for your code, make it easy for people to use. We'll talk about the principles of reactive programming next week, because that you kind of need to understand that to build these things, and then some of the options for deploying them, right? So we're going to cover a lot. This is pretty ambitious. We may or may not get to everything, but we'll do our best. This is the first run of a workshop, but we definitely don't have time or the background to cover a lot of other important issues. So what we're not going to cover in any depth, at least, as you probably know, there's a lot of details with weather data, with degree day models. So we're not going to talk too much about the scientific or statistical assumptions and limitations of degree day models, for example, like how they're parameterized, where they were parameterized, the assumptions, the uncertainty that these models provide in the predictions they make, right? I would encourage people to voice and share those kinds of questions, maybe share some resources as they come up. Well, likewise, with weather data, right? There's practical limitations. We will talk about what makes for good weather data for doing these models, for making predictions of biological organisms. But there's a lot of details there. I'm certainly not the expert there. Or the weather models, right? So where we're talking about future predictions, there's a lot of details about bias and uncertainty and how you handle that, how you present it, and so on and so forth. There are a couple of experts here on the call, though. Those questions come up. So please voice these things. We do want to take note of them. It's part of being responsible. We are building or working towards decision support tools. So to the degree that it behooves us to be transparent about the quality of the support that we're providing, because presumably the goal is to support decisions that are useful for growers or policymakers or researchers. There's some technical aspects that we're not going to get to, such as some strategies for downloading and republishing weather data. So a lot of weather data providers don't have an API necessarily, but they might share files, maybe tabular files, database files, raster files. And if you want to use those in a tool, then you have to download them or get access to them, probably wrangle them and republish them. But that's a whole nother can of worms. There are some other weather data resources out there that are not through APIs, but there are through services that you can access, you can query through like ArcGIS. There's a lot of open data on Amazon right now and other cloud providers that you can query if you know how using GDAL. We're not going to talk about that stuff. We're only talking about APIs today. We're not going to talk about working with modeled climate data decades out. There's some statistical and best practices there. We won't talk too much about how you can manipulate the results of predictions and kind of transform them into more usable information for your audience, such as putting things into probabilities, that kind of stuff. Daisy chaining some of these models together, and then some of the more intermediate against you. So what we're covering today is a really good start, but it's just the beginning for, there's lots of room for continuing on, okay? So in case we run out of time, which I always do, here are some of the take-home messages. First of all, degrading models are widely used to predict the phenology or the development of plants and insects. All right, so they're decades old. This is not new. People have been using them for a long time, certainly in research, in planning, and crop management decision support tools. So they're among the best models that we have. And I should say they're a subcategory of weather-driven models, right? Because there's also like other kinds of models that predict the needs or the development or the phenology of crops and insects that also use maybe chill or irrigation requirements and other stuff, okay? Degree day models require you to get temperature data, right? That's the inputs, is temperature, either daily or hourly temperature data. And you're probably going to have to manipulate that data to get it into the right format to feed into a model and to present in a decision support tool, right? R is a really, I mean, that's R's forte. R is fundamentally a computing environment to manipulate and work with data. So it's really well equipped for all of this. You can use it to wrangle data, to compute degree days, and to make predictions, right? APIs have made things easier to work with weather data, to get weather data into R, but that's still a speed bump, right? There's still a lot of details involved in working with weather data. We'll see some of that. And another take-home message I would say is that Shiny is a really good tool for creating these decision support tools. It dramatically simplifies the amount of knowledge you need to create a web app. And it's relatively easy to publish these as well, right, to deploy them online. Right. So if you don't remember anything else, I would say these are kind of like the non-technical take-home messages of what we're going to cover. And please chime in here, everybody, if you have other thoughts or questions. Okay, so with that, and you know, before we go into a notebook, I want to share. I want to talk a little bit about degree days. The slides aren't fully finished. I'm going to be mixing and matching here some different presentations. Can people still see this slide? Can you still? Okay, thank you. All right, so let's talk about like what are degree days. So first of all, degree days are a model that the broader family of models that you might think about these would be models that use thermal units. That's the terminology. And it's simply thermal unit, which degree days is an example of that. It's simply where temperature accumulated over time is a good predictor of something, right? So that's the key thing. All of these models that are built on thermal units look at temperature and time and combine them together. So that includes degree day models, which we're talking about here. I'll talk about some of the other ones in a bit, but growing degree days, that's another one. Growing degree day models are often used for crops or plants specifically. Degree day models do a little finer job of measuring, a little more precise job of measuring that accumulation of temperature over time. They're often used for insects and other kind of organisms. There's heating day and cooling day models, degree day models are developed from the energy sector to make forecasts about energy needs into the future. But they're all similar, right? They're basically aggregating some measure of temperature or chill over units of time. Right. So let's talk about degree days specifically. So here is a working definition of what a degree day is. It's a metric of the usable heat that a specific plant or insect can utilize to develop accumulated over time. So let me highlight a couple things from this definition. First of all, we're talking about a metric. This is not something you walk out to your weather station and you see a dial that tells you the degree days. It is something that's been derived by researchers because it's useful in science and in modeling, right? But it's not a physical measure. So that's point number one. Second, it's a metric of usable heat. So in other words, if it's really, really cold, your insect's not going to do much, right? Or your plant's not going to do much. Likewise, if it's super, super hot, the insect or the plant's probably going to shut down, right? Because it has to cool itself. So for most organisms, that are ectothermic. This is an important thing, right? All plants and insects are cold-blooded, right? So their development rate is really, their metabolism is really based on the ambient temperature, right? But that's within a specific range, right? Their metabolic processes are influenced within a temperature range, upper and lower bound. That means that these metrics are really specific to a specific plant or insect, often a specific cultivar, right? So there is no such thing as a one-size-fits-all degree day. They're always computed in reference to a specific plant or insect or a plant-insect system. So for example, navel orange worms on pistachio, navel orange worms on almonds. Those are different systems, and you might calculate, and you certainly would use the models for those two systems differently. So these models are good for predicting development. Now that development could be a continuous property, such as something like hull volume or hull hardness, for example, something that you can measure continuously, or something which is discrete, right? Such as going from an egg to a larva, or from a larva to an adult, right? So discrete stages of development, right? Different models predict different things. Finally, accumulated, the reason that this metric is accumulated over time is because that reflects the physiology of these organisms, right? So for a bud to become a flower, little physiological processes have to go in there, the development of proteins and sugars and I don't know what, but it takes time for that to happen before that phenology event can happen, right? So that's why these models accumulate the temperature over time. And then the time, time is continuous, but in practice, these things are either going to be measured in days or hours, okay? Because that's how the data come in, as well as that's where you get a good balance between, sort of complexity and the amount of data and prediction, all right? So in a nutshell, that's kind of what degree days are. There's a couple ways. So there are many ways there are many variations of how we compute degree days. So oftentimes we only have minimum and maximum temperature to work with, certainly with the older data sets. So what researchers have done is they've come up with models to estimate the amount of temperature over the course of a day, right? So a common one is a sine model, which is what we see here. And as you can see, in the graph here, that there is there's an upper threshold and a lower threshold. And again, that's going to be for a specific organism. All right. So this is how we can take maximum and minimum daily temperature and compute this measure of effective temperature accumulation for each day. Right? Now, that being said, there's a lot of variations. So here are some of the other methods that researchers have come up with to, again, go from minimum and maximum daily temperatures into a better, kind of more nuanced measure of temperature within that day. So you're going to see these method names: single triangle, double triangle, single sign, double sign. We don't have to go into great details here, but this is sort of the foundation of, and this is why they're different ones. Now you might think, well, why are there so many? Like, does it really make a difference? And researchers over the decades have tried to find the best ways, and when they publish their work, they've found, some researchers say what fit our data the best, or what gave us the best prediction, was the double triangle method. And then you have to use that if you want to use their predictions from their model, right? So this is the essence of it. Now, that being said, though, computing the degree days from those formulas, it's a little bit tricky. These graphics here are from Zolom et al. 1983. I don't see Professor Zolom here, but he's still active and wrote the seminal paper. And these are the equations that are being computed under the hood to compute degree days for these methods. Now, something else which is really important to actually work with degree days, of course, you need a source of weather data. You need those upper and lower temperature bounds, but you also need to know, like, when should I start counting, right? Because we have to start counting these things up to predict when the flowers are going to blossom. When is the best time to till your soil, right? If you for certain kind of application. So that event, the date when you start, it's generally called a biofix event. And sometimes it's something that you might observe, such as when you start seeing eggs on your sticky paper traps out there in the orchard. You should be monitoring. And then when you see that, then you can start counting up the degree days to figure out, when's the best time if you need to do an early pesticide application, like when's the optimal couple days to work on that? Or when do you expect to see the adults or the eggs? And then again, that's another time when the different IPM methods might be effective. So you need that, and then you need to do these calculations using either a really big sheet of paper in your calculus book, or in our package, or a computer program. All right. Okay, so yes, this is just to highlight that these things are not useful by themselves, but they're always done in reference to something else. Okay, so enough of that. Let me close these up. And one more thing before we jump into our notebook, I want to talk about notebooks. So right here. So we're in a second here, we're going to go into Posit Cloud, and we're going to start working on some code, and we're going to be working in notebooks. So depending how much you've spent time working in R, you may or may not have been worked with Cordo notebooks. But this is what they look like when we open it. And I just want to highlight some of the bells, some of the buttons on here. So a notebook, it's a little bit like a script, right? It's plain text, and it does have R code in it, but it also has other stuff. At the top of your notebook, you've got a section that's called the YAML. Just leave that part alone. That just kind of tells RStudio what kind of notebook document this is and what are some of the options. You're going to see various formatting, so that when we save this as HTML, this formatting will look nice. It'll become headings, it'll become bold, it'll become bullets, and so on and so forth. So you're going to see a lot of that markdown formatting, but the code, the R code that has to be valid R code is going to be in these little gray boxes. They're called code chunks. Right? So you're going to see those, and almost all of them are ready to go in the notebook. You just have to like run them, which we'll talk about. So, and the way you run them is there's a couple buttons that you, first of all, you click in the code chunk. If you want to run them line by line, you can click that little run button up in the toolbar. When you run code in a notebook, if there's output from that code, it's going to appear below it in line with your notebook document, as opposed to down in the console or as opposed into your plot pane over there. So, but you can change that if you want, but the default is to display it in line. If you want to run an entire code chunk, there's another button that you can click. You can also hit Control-Shift-Enter, and that'll run the entire code chunk. And it's important to note though, when you're running code in a notebook, it's kind of sandbox, right? So what you've done in your base environment doesn't help. So you have to run the codes from top to bottom. But you can run all the code in previous code chunks by clicking this little button here. And then there is a render button that you're going to see as well. And when you click the render button, it runs all the code and saves it as an HTML file that you can then keep forever. And that HTML file has all the code and all the text. And that's kind of like you put that in your personal library that you can come back to. All right. I think those are the details. All right. Any questions? Okay, we will take a break, but let's keep going so that we can at least do our first notebook. And I'm going to put in the chat window here a URL to Posit Cloud, right? So at this point, open up Posit Cloud, or first of all, click on this link, and then I'm going to click on it too. Let me open a new window. So it is a Posit Cloud link. It will ask you to log in if you haven't logged in. If you haven't created your Posit Cloud account, at this point, I would just say, just watch. You'll still pick up quite a bit. This Posit Cloud will be up there for a long time. And all of the notebooks that we're going to look at, they're also on GitHub, and they're rendered on GitHub. I'll put the links in our webpage shortly. But assuming that worked, you will see a new project in your Posit Cloud. It should open up. And the very first thing you should do is click that little button that says Save a Permanent Copy. All right. So go ahead and click that, because otherwise you're just working on a temporary copy. It's basically a clone of this project. So if you're not opening the original project, which is in my account, but it's making a copy for you, putting it in your workspace, and then inviting you to save a permanent copy of it if you want to keep it in your workspace. All right, let me pause there, and could people give me a thumbs up in the chat when they've managed to open up this Posit Cloud project? And when most people, or a lot of people, if you're having trouble, meaning like there's an error message, it looks like quite a few people are successful. Okay, very good. Is anybody, if anyone is using RStudio Desktop, I can also, I can send you another link you can use to import this project in RStudio Desktop. Okay, so go ahead and click on the exercises folder. I assume everyone's a little familiar with RStudio, so I'm not, but if you have questions, feel free to put them in chat. But go ahead in the files pane, which should be in the lower right if you haven't changed your windows around. Click in exercises and click on exercise 1, degree days QMD. So QMD stands for Quarter Markdown. This is the newest flavor of Markdown that's been developed by Posit, the company that now manages RStudio and Posit Cloud. It's really, really similar to our Markdown notebooks and our Markdown files. So if you've worked with those at all, it's really, really similar. It's got a more rich set of options in the YAML, which I think you'll see when you open it up. Yeah, so I'm just going to go ahead and talk through the code in this notebook. I am looking at it in source editing mode. So you might notice up at the top, you can edit this in source mode. That's what I'm going to do because I like to see all of the Markdown and the code that's actually running. You can also run it in visual mode, right? So if you prefer what you see is what you get, click on there and that should work as well, right? Okay, so let's come down. So what we're going to do in this notebook is we're simply going to import some weather data from 2023 for a CIMIS station in Napa, California. And then we're going to compute degree days for a specific model that some of our farm advisors up there and colleagues at Davis have developed to predict the best time for a vineyard owner to till the soil to break the life cycle of a bug that's a vector for a disease that affects plants. So that's in the big picture, that's what we're going to do, right? So we're not importing data from weather APIs yet. We'll do that in the second half. Okay, so come down to code chunk number 1. Just scroll down. You'll see code chunk number 1. Click inside it, and then hit the little button that says run this code chunk. You could also do Control-Shift-Enter if you're on Windows, or Command-Shift-Enter if you're on a Mac. And basically all we're doing here is we are defining the path to a directory inside this virtual environment. You might notice inside the exercises folder, there's another folder called data. That's where the data files live. Go ahead and then come down to code chunk number 2 and run that as well. And here, what we're doing is we are simply we haven't imported anything yet. We're just creating a path to a CSV file and verifying that that file actually exists and that we typed it in correctly. So this is just some programming methods for importing data, some preparations. And then come down to code chunk number 3, where this is where we are actually importing this CSV file and looking at the first 6 rows using the head function. Okay, so here you can see what the data look like. So for each day, starting from January 1st, 2023, up until June 30th, 2023, we're getting the minimum and maximum temperature in Fahrenheit from this weather station in Oakville, Napa Valley. If you're curious, like, how did the CSV get created? The file that I ran to download the data from the CIMIS API is in the scripts folder, right? So if you want to see an example of code to import data from a CIMIS station using the CIMIS API, you can look at that script, and you'll see how it also did a little cleaning up there. But that's so now we have some data. It's roughly 6 months of daily data that we have in our table. So go ahead and scroll down. The next thing we have to do is actually pick a model, right? You can't do anything, you can't do much more until we've picked the degree day model. Because remember, the degree day model specifies some very important things. It specifies, let's go down here a little bit. It specifies what you're being predicted, what's being predicted. In this case, it's a recommendation for when to till the soil for this IPM method, when to start counting, right? So that could be, in this case, it's a calendar date, right? Sometimes it's something you see in the field. It tells us what method that we should use to compute these degree days, starting from the biofix. The lower threshold, the upper threshold, the cutoff method, these are the details of the different methods that we can use. And then what is actually being predicted, or when the predicted event happens. In this case, it's a range of accumulated degree days. Okay. So that's the model. This little graph, what you should see it in your notebook. This is a screenshot from Cindy Cron, one of our IPM advisors presented this model a couple years ago. And you can see the two little shaded regions. The pink region, that's the date when you see the little baby nymphs based on the the temperature. And that's the ideal time to till the soil because the nymphs are they don't have their wings yet, and you can knock them down enough to control the population just by tilling the soil, which you probably have to do anyway. And then the little yellow bar represents again the range of degree days when you would see when it's predicted to see adult nymphs of this three-cornered alfalfa hopper bug. Okay, so those are the predictions for this model. There are 2 degree day ranges, one for the recommended window for tilling the soil, and the other one is when you would predict to see adult nymphs. I should also state that if you look at the paper from this model, this is based on a simulation, right? So they developed a simulation of the life cycle of the three-cornered alfalfa hopper and ran it. So it's a little bit different than some research, which is it's based heavily on field observations. But this one, it's a little bit more nuanced. Okay, very good. All right, so let's keep going. I know that I'm blowing through some of the text, but when we save this to HTML, we'll get a good look at that. Code chunk number 4, come down to code chunk number 4, click in there and run the whole thing. We are loading dplyr, which is one of the go-to packages for data wrangling from the dplyr or from the tidyverse. Also using here the conflicted package. So the conflicted package is how we avoid function name clashes, right? So dplyr has some functions like filter, count, select. These are really, really generic and popular names for functions that might exist in other packages. So this conflicted package allows us to state our preferences when these functions are being used, and we're just simply telling R to please use the version from the dplyr package and not some other package that we might just happen to have in memory. Right? It's kind of preventative maintenance. Okay, coming down to code chunk number 5, go ahead and run that. Click in there and run it. We are loading the degree day package, which, as you can guess, it's designed to compute degrees, and that's all it does. It's written by yours truly, and there's a website that talks about all the functions. I should also say the degree day package. We've also set up a code validation repository using the reference code from the Zollum paper from 1983, as well as reference data from the UC-IPM website, which is kind of a reference for most of these things. Code chunk number 6, go ahead and run code chunk number 6, and then we'll pause here and talk through code chunk number 6, because this is where we are actually computing degree days, right? So the model for the three-cornered alfalfa hopper states that we should use the single sign method. So we are using a function from the degree day package called dd single sign. The arguments that we're passing into it is, first of all, a record time series of the minimum daily temperatures, and that's saved in the Tasmin column of the data frame, right? So we're using the mutate function. The mutate function is the function from dplyr that you use to add columns to a data frame. So we're going to use that column for the minimum. There's another column there for the maximum temperature. We also have to pass the lower threshold. And again, the research tells us what number to use for the lower threshold. In this case, it's 32 degrees Fahrenheit, as well as the upper threshold. This model does not have an upper threshold, so we simply put in a really big number. So that's what that part of the mutate expression is computing. It's adding that column. And then right below that, we're adding another column to the data frame called the accumulated degree days. And that's, again, it's going to add another column to the data frame. You can see it in the results. And we're using the cumulative sum function to add up the daily degree days to get the running sum. All right. So that's how code chunk number 6 works. Okay. Any questions?
Yes, question about this.
Yes.
So the function that we're using from your package is that DDSNGSINE.
Yes.
And then, okay. And then you're wrapping that inside mutate and inside some dplyr things.
Yeah, so the only dplyr function that we're using here is mutate.
Okay.
Yeah, so mutate is the function from dplyr that you can use to add a column to a table, to a data frame or a table. Yes, and these I didn't highlight it, but we're using piping syntax here. Right? So I'm using piping syntax, which is basically it's an alternative way of writing of chaining functions together. Right? So we're basically piping the data frame into the mutate function, and then it kind of pops in automatically as the first argument. So we don't have to write that first argument because mutate expects as the first argument a data frame, and then the subsequent arguments for mutate are the expressions that generate these new columns. Okay, so yeah, it's a fairly standard approach to adding columns, and you can see below. You can see the and below underneath it, you can see the results, and we should see. I said this is going to be January through June 2023. So I can, if I go to the very end of the data frame, I can actually see the running sum of accumulated degree days, right? So as of June 30th, the accumulated degree days for this species, for this location, was 3935. Right? And again, that model that we're using to make predictions gives us a range of degree days when different things happen. All right.
That's cool.
Okay. All right. So now we've done the hard part, right? We've crunched the numbers. We've computed for every day the degree days from that day. That's DDF, right? So the number of degree days that accumulated on a specific day. And then we're also accumulating them, adding up according to what the model tells us to do, which means start counting from January 1. Okay, so the next thing we should do is identify somehow when, the specific dates when those thresholds are met, right? Because the person who's going to use our decision support tool probably doesn't care about the accumulated degree days. They probably want to know, when do I need to get the tractor ready to do the tilling, right? Like what range of dates. So that's what we're going to do in the next section. And to do this programmatically, we could simply go through the table that we just generated and actually just kind of visually look, when do we hit, what was the number we're looking for? It's like 2358. All right, so when does 2358 start? And a lot of decision support tools, that's exactly what they do. They present you, here we go. I can see it looks like around May 11th, roughly, right, is when we hit that magic threshold. And a lot of decision support tools, they do just present that table, and then you can scroll down, and you have to kind of remember what your number you're looking for is, and then find it, and then that's how you know your date. But we can do better than that. So in code chunk number 7, go ahead and run code chunk number 7. What we're doing here is we're creating a custom function that we are going to, it's called till_yn. And it's simply, it takes a single argument x, which are going to be a number. And then if that number is greater than 2358 and less than 2817, this function is going to return true. Otherwise, it's going to return false. All right, so And then we're actually testing it also in code chunk number 7, just to make sure it works. And if you look at the results of our test, yes, when we can see that at 2800, sorry, at 2400, 2500, up to 2800, we're getting trues. And then the other, values outside that range, it's returning false. So we're going to use this custom function, very simple little function. We're going to use it to populate a new column in our table. Right, so that's code chunk number 8. So go down to code chunk number 8. Again, we're using the mutate function from dplyr. And then inside mutate, we're writing an expression that defines the name of the new column and then how to fill the values of that new column. And you can see it there at the end, the first few values. So now that new column till will have true or false if the accumulated degree days is in that magic range that we're looking for. Okay.
Oh, yeah.
So code chunk number 9, go ahead and run code chunk number 9. And the filter here, we're using the filter function. So we're taking our table that has that new column and we're piping it into the filter function from dplyr. And the filter function expects as its argument a logical a vector of logical values or an expression that returns a vector of logical values. And we're simply using it to subset out the rows where this condition is met, right? So it's a pretty simple construction to filter out based on that column. And what we see as the results here, we're not saving these results, we're just printing them to the notebook. We can see the range of dates when the accumulated degree days fell within this range. So from May 11th up to May 24th. Right? So we're getting to figure out like how can we programmatically present these range of dates to the user of our decision support tool. Right? Code chunk number 10, go ahead and run that. And here we are simply pulling out the dates as date objects, and then part of our decision support tool could be a little sentence or somewhere in the website saying based on this record, we recommend that you till your soil between May 11th and May 24th. Okay, so that's one way that we can take these dates and then feed them into Shiny app. Okay. Questions? All right. Yes. Thank you. There is a GitHub site there too. Okay. Thank you. Okay. I'm going to blow past challenge number 1, but basically, what it's asking you to do is find the dates for. Actually, no. Why don't we pause here? Let's pause and do challenge number 1. So your job in challenge number 1 is to identify the dates when this model predicts that we would see adult nymphs in the field. Right. So what we just did was we identified the dates when the baby nymphs are out, but there's another range of accumulated degree days, specifically 3137 to 3447. So my question to you is for this data set from 2023, when were those dates? When were those accumulated degree day values reached? All right, that's similar to what we did above. So let's pause here for a couple minutes and let folks work on that. There is a bit.ly link there too that you can click on if you want to see the solution. See, we have an answer in the chat window to the challenge. It's good to meet Prakash. Would you want to share your code that you used to? Okay, we're getting some other folks. Would somebody want to share their code that they used to come up with this, and then I'll copy paste it and see if it works for me also. Okay.
Yeah.
All right, so I'm gonna put in oh, several people got it there. All right, so Mukesh, I'm gonna put in Mukesh's code here and we'll look at it and talk through it. All right, so again, we're looking at the solution to challenge number 1. And the first thing that we're going to run here is we're going to create a function that we can then use to add a column for when the adults are present. And it's based on the function that we use to define, if the for the tilling range. So that looks perfect. Adults adult yn. Then we're going to use that function inside mutate to create a new column. Again, that's the perfect thing to do. Maybe I can just I'll just run that by itself, and we can just take a quick look. Yep, there it appears at the end of the data frame. And we save that to a new object, a new tibble called Oakville Adult TBL. And then to pull out the actual dates, we take that tibble, we use that adult column, which is true false values, inside the filter function from the applier. So at this point, all we have are the rows where that column is true. Next, we pipe that result into pull. The pull function grabs a single column from your data frame. In this case, the DT column has the dates. All right, so now we have a column of dates as a vector, no longer as a data frame. We pipe that into range, which returns your minimum and maximum value. And for dates, that's the first and last dates. And then we use the assignment operator to save that in a new variable called adult dates. And then we look at the values of those, and we get June 5th through June 14th. Okay. There are other ways that you can do this as well, but this is certainly gets there pretty quickly. All right, well done. Several folks got it. Excellent. Okay, let's keep going then. And let's talk about, okay, so now we've computed, we figured out the dates when these things, how are we going to show this to a user in a web app, right? Which is kind of what we're ginning up code that we'll use. So a common way to visualize degree days and when things happen is simply to present a table. So in the next code chunk below that, that's what we're doing here. So using the table function, which is a function from knitr, which is just simply designed to present a data frame as a table with some formatting options. So we could put this in a website, right? We could have this appear magically, and a lot of websites that are computing degree days for folks have tables like this. We could make it look a little bit nicer. We could put in grid lines and that kind of stuff. But it's kind of a long table, so all the information is there, but it kind of requires somebody to like scroll down and manually look for the numbers. So we can do a little bit better than that. So coming down to code chunk number 12, go ahead and click in code chunk number 12 and run that. Now, if you get an error in code chunk number 12 because you didn't run something previously, like you forgot, or again, you can click that little button that says run all the code chunks above it to kind of catch up. That'll run everything above it again, and then you should be good for code chunk number 12. If you scroll down and look at the results of code chunk number 12, it's a table, but it's a little bit more elegant and nicer looking than simply a really long table. You can control, there's a drop-down box to determine like how many rows you want to have it. And there's some other options that we can use to make it look nicer. And you can see some of the options that we've used. So we are using a function from the DT package, right? Which is designed for this. Yes, Adrian, you had a question? I'm not showing the screen. Really?
Yeah.
Don't know how that happened. Thank you. Please speak up when that happens. Okay, thank you. Thank you for that. Yeah, please speak up if my screen share goes away. I'm not sure when that happened. Okay, so code chunk number 12, run it again. And yeah, so we're basically using the DT package to make the table look a little bit nicer. Okay, and you can see some of the options that we're using from the data table function. This function allows you to specify column names, nicer looking column names. It allows you to provide a caption to your table. We can we're hiding the row names, auto hide navigation that hides. There's a little thing down there that we didn't need actually this time. And you can set the page length. You can tell it whether or not you want to have the search box. The data table tables have lots of options for interactivity. It's a well-developed JavaScript library that this function is using to present this table in an interactive table. But there's one more thing that we can do to make it even look a little bit better, and that's conditional formatting. So if you click in code chunk number 13 and run that, we're also using the data table function from the DT package, but here we're adding format style to format the rows that in this case show the dates when that range of accumulated degree days falls within the recommended range for tilling. So if I come down here and scroll through my table, I can see when I get to May, some of the rows appear red, right? So that kind of visually highlights the degree day values that fall within that range, right? So this is another tactic that we can use to present the results of the predictions of our model to a user, right? It's still a little clunky though, right? It's a table and you have to go through a lot of stuff. The next thing that we'll do in code chunk number 14, come down to code chunk number 14 and run that. And here we are going to use, a plot. We're going to make a plot because this is a use case where a plot would probably do a nice job at showing the recommendations, right? So in code chunk number 14, the first thing we're doing is simply plotting the accumulated degree days over time. We are using ggplot here. So you might remember ggplot plots are created by the opening move is using the ggplot function where you provide your table. And then the second argument there is going to be how the columns in the data frame should get mapped onto the features that are added to the plot. So in this case, we're saying the X values should be coming from the DT column and the Y value should be coming from the accumulated degree day column. Right? So that's what the mapping function or mapping argument does. And then if we stop there, it's not going to show anything. So you have to then add a geom to it, which is actually the function that puts things onto the canvas, that draws things on the canvas. So that's code chunk number 14. Next, go into code chunk number 15, and we're doing the same thing, but here we're adding another geom, a rectangle, where we're kind of like manually specifying the X minimum and maximum and the Y minimum maximum for a rectangle. Right?
Hey, Andy,
Yes.
if I can stop you for a second, I don't know about others, but I'm getting an error on this line about a conflicted filter.
Oh, you know what you should do, Shane? Click the little run all chunks above. So filter is one of those functions that exist in multiple packages, including the stats package, which is part of base R. So that conflicted package, which you probably should run it again, tells R to use the filter function from dplyr.
Okay.
Did that? Yeah, give that a shot. And then,
I'll give it a shot and I'll report back. Thanks, Andy.
okay.
Mine did go through, so.
So it's just me.
Yeah, same. I mean, it doesn't have, the code doesn't have problem, no.
Okay, good, thank you. I just wanted to make sure and get it addressed if it was an issue.
Cool. All right, so this is another example of a visualization that we could put onto our decision support tool, which does a little bit nicer job of showing the the range of, in this case, the accumulated degree days, the dates when those are reached. All right, and then finally in code chunk number 16, go ahead and run that. It's the exact same plot, but we're just tacking on a couple more helper functions to our ggplot. And you can see them at the bottom. We're using the labs function, the xlab function, the ylab function. We're just adding them on. And these are setting some of the labels for the axes. Okay. So ggplot is a pretty nice, it's a very powerful plotting package, very popular. You can do lots of customizations. You do get a static plot. So next week, when we look at Shiny, we'll also look at Plotly. So Plotly is another package that you can use to make plots, but the plots that Plotly produces are interactive. So like you can hover over the line and see the coordinates around it. So it kind of lends itself to an interactive web app. Okay, questions. I know this is going quickly. Yeah, there we go. Okay, so let's go back to our slides. And let me go back to our master menu and open up the next set of slides and talk about weather data, right? Because what we just did, that was the easy part, right? It's not hard to compute. Once you have weather data, it's not that hard to compute degree days. It's not that hard to compute accumulated degree days, and it's not super hard to identify when a prediction event happens, right? Or to feed that into some sort of growth model. But we have to get weather data. So that's what we're going to talk about next. And the good news is that there are more APIs out there available. The bad news is that we're not going to have time to get very far. But let's talk a little bit about what makes for good weather data. And then I'll jump right into a notebook. Actually, I'm just going to jump right into a notebook, right? Let's talk a little bit about what makes good weather data. First of all, weather data are not all created equal. If you're using them for predicting the development of plants and crops and insects, right? The data from the big international airport is probably not going to be the best representation of the temperature in the orchard, right? So here's a question: is hourly data better than daily data? What do people think here? If you have your choice to get hourly data or daily data, is hourly data always going to be just better somehow?
Is the daily data one reading per day or the average for the day?
Oh, good point. Well, it would probably be the minimum and maximum, but that's a good clarification. In general, hourly data is more precise as it's finer temporal resolution, but it all depends on the model that you're developing, that you're using, right? So if the researcher who developed the model, whose predictions you're using, use daily minimum and maximum, then that would be the data stream that you would want to use. So you can get hourly data, and that's becoming easier to do. However, you're just going to have to resample it to daily data anyway. So the answer here is it depends, right? All of these, it depends. Is data from a weather station which is close by always going to be better than weather station data that's farther away? All right, we have one person saying yes. Any other thoughts? It depends. Okay, it's a safe answer. It's not really my field. I would say yes. right? I can't think of a scenario where you wouldn't want to get data that's close to your farm than farther away. Unless unless your farm is like right on the middle of, like on the edge of a mountain or something, and the data on the other side of the mountain might be physically close, but it doesn't really represent because there's a different microclimate over there. But in general, probably yes, right? That being said, though, it depends, right? Like if you might have a weather station on top of a school or a hospital that's 1 mile away, and there might be a weather station in somebody else's orchard 5 miles away, the orchard might be a better representation of what you have in your orchard, right, or your field. So it depends. It's true, fact or fiction. Interpolated values at your location are going to be better than a measured value if that station is farther away. Obviously, that depends, right? It depends on the interpolated surface, right? Is it capturing the microclimates? Is your farm within a microclimate where that's important to capture? How far away is the other station, and so on and so forth, right? But yeah, but there are raster surfaces out there that are interpolated between weather stations, and those are becoming increasingly common, as we shall see. Is free weather data always better? That also depends. There tends to be an inverse relationship between the cost of the data and the reliability and performance of the system that's getting you the data, right? So, not necessarily. There's some great publicly available data that's provided in a really high-performing API, but a lot of it's expensive to maintain weather stations. It's expensive to provide the data through the cloud, through cloud services. And if you want it to be sustainable and reliable, sometimes the private sources that do have a subscription fee are going to be more reliable. So all of this depends. So me and my colleagues have started to put together a spreadsheet of weather data sources that we're familiar with. So if anybody, I would appreciate any people, if you have comments, would like to add something to this sheet, please feel free to do so. But the ones that I'm gonna talk through here quickly, that we're gonna use in our next notebook, I'll mention just a couple of these sources, these cloud sources, these online sources for weather data. So CIMIS in the state of California is a popular network of agricultural weather stations. There's roughly 150 of them. They tend to be in agricultural areas. I do believe this system grew or evolved out of ANR research. So, but it's currently managed by the Department of Water Resources. One of the things that people like about the stations in this network is that they are supposed to be on well-watered grass. So it's kind of like a controlled environment. There's a standardized kind of local environment, which means that you can also use the temperature and humidity and solar radiation values that are measured to estimate reference evapotranspiration over the grass, which is called reference evapotranspiration. And there's ways that you can use those values to estimate the water requirements of a crop, which is not grass, but there's a known relationship between the water requirements of the grass and the water requirements of the crop at its stage. So that's partly why Water Resources manages and pays the cost for this set of weather stations, because it helps their core clientele, which are irrigation managers. Another reason people really like the CIMIS network is because the data are available for free, including the API, which is good and bad. It's good because it's available, it's paid for by taxpayers' dollars. The bad thing is that it's a little bit oversubscribed, and when it works great, but it oftentimes does not work, and you don't get any kind of advance notice, and that can happen kind of randomly throughout the day. So it's not the most reliable API. They are giving it a pretty big makeover this year, so hopefully a year from now, this will be a better source. All right, so that's CIMIS. Another one is called Synoptic. Synoptic is another source of weather data. And it's pretty, it's very high performing. And I asked everybody to create an API key for Synoptic. It allows you to download through an API weather station data from tens of thousands of weather stations across the country. So essentially their business model is to aggregate data from weather station networks, do some cleaning, do some quality control, do some standardization of the weather variable names, and then make it available to their customers through an API. And it seems to be pretty popular. If there's a need for that kind of service, they are public benefit corporations, so they do have a fairly generous allowance or quotas for the open access platform, which is including what academics can use. All right. Open Medio is another newish, it's at least newish for me, weather API. And this group provides an API access to all kinds of modeled weather data products, including the 7-day forecast. They even have a seasonal forecast, which we will look at shortly, as well as historic data. And don't know a whole lot about the people who, or the organization that runs Open Medio, but they're basically using existing models from National Weather Services to generate these raster surfaces. There's some big cloud computing that they're going on. And they also have a generous free tier for using their API, right? So it's a good choice for like your 7-day forecast. And there is a art package for it. And then finally, a CalAdapt is another source for weather data. There is both modeled climate data, past, present, and future, as well as observed data from the past. And CalAdapt has a well-performing API, and there's also an API package for CalAdapt. So, any questions or additions for weather data sources? Okay, question about is Synoptic pulling data from NOAA? Good question, Adrian. Off the top of my head, I don't know if NOAA weather stations are ingested into Synoptic, but I would say what their niche is station data. If there are, and you know, weather forecasts tend to be modeled rasters. Open Medio definitely has the NOAA weather model products. So I think we should stop there because we're at time.